This presentation considers the history, site analysis, user intervention, and ecological benefits that the zoo has to offer, and also considers the shortcomings that can be improved on to transform the zoo into a crucial biodiversity node within the Tshwane region.
The history of animals in captivity dates back to the time of the Egyptians. Contemporary zoos are based on models from the 18th century. After World War II, we find the birth of modern-day human rights, and from the 70s onwards, animal rights are introduced. A divide exists between what the zoo does and public perception of its role. From our assessment, the following areas hold promising opportunities for intervention. On a north-south axis, the site combines a ridge, a river, and a stretch of land towards the inner city. Although the city of Tshwane has a moderate climate, there's a steady rise in temperature seen from 2000 onwards. Furthermore, urban heat island effect can add 6 degrees Celsius to urban areas. A shadow study reveals that the proposed site is exposed to solar radiation and wind. As per zoo authorities, access to clean water remains a constant struggle, as is also indicated by 6 boreholes on site. Katabatic winds due to the ridge hold potential for night cooling. By using a standard Olympic-sized swimming pool, we determined that the zoo, site-wide, can collect the equivalent of 190 Olympic swimming pools in annual rainwater harvesting. Based on estimate municipal water consumption, the Pretoria Zoo can collect 6 times its current municipal consumption. Out of the zoo's 9 stormwater systems, roughly 22% of stormwater passes by the proposed site. River intervention is proposed in the form of riparian restoration and the introduction of wetland systems to filter river water.
The zoo is built on a geologically rich landscape with granite, sandstone, and shale formations shaping the terrain. These diverse soil types, loam, sand, clay, and rocky soils, create a strong foundation for different ecosystems, allowing both plant and animal species to thrive in their ideal environments. Because of this unique geography, Pretoria supports vegetation within the Gold Reef Mountain Bushveld bioregion. The terrain plays a key role in plant distribution, with denser woodier vegetation on slopes and an abundance of grasses and shrubs that serve as food sources for wildlife. These ecosystems are protected under the NEMA Act, ensuring biodiversity is preserved. As we move through the zoo, the vegetation shifts with the topography. Along the ridge, riverbanks, and cultivated areas, we find native plants like the baobab, the bird of paradise, and the wild garlic. However, invasive species like the lantana camara threaten the balance of this ecosystem, making active conservation efforts crucial to maintaining biodiversity. Just as the vegetation is carefully managed, so is the movement of wildlife. A green corridor is proposed to reconnect habitats and support small mammals, birds, and insects. Species like bush babies and porcupines will benefit from these linked environments, allowing them to move freely and thrive. Incorporating traditional medicinal and edible plants like the Artemisia afra adds cultural and educational value. These species have been used for generations and connect modern conservation with indigenous knowledge, making this project not just about wildlife but also about community engagement and sustainability.
In terms of social considerations, the visitors of the zoo include all age ranges, but predominantly families with children, and the main preferred mode of transport is a personal car. Throughout history, we can see how urbanization has slowly started fragmenting and reducing natural green spaces across the Tshwane region. This is important as one of the main reasons people visit the zoo is for different experiences from their day-to-day, so the zoo has an important role of ecological connection. Another main reason to visit the zoo is for the connection with others. 68% of visitors attend the zoo with children. Children are seen attending weekdays on school trips as well as with families on weekends. The main entrance poses a problem, with Boom Street being a fast-paced, high-traffic area not suitable for pedestrians, so people rely on personal cars for transportation. So the question is, what do we do with this information? Examining the KWP master plan, we can see that various issues were addressed. These included rethinking water cycles, implementing a new entrance to improve pedestrian safety, and introducing a range of interventions that will improve the zoo overall. Based on our mapping, we have created a sensitivity map identifying 3 main sensitivity zones. High sensitivity zones, located on the northernmost part of the site, are high-risk areas where development is strictly prohibited to preserve ecological integrity. Medium sensitivity zones, primarily in the northwestern area, are ecologically supported and require minimal intervention to maintain their balance. Low sensitivity zones, found in the southernmost part of the site, are not ecologically supported but also do not pose significant risks, making them suitable for development and intervention. Our SWOT analysis highlighted key strengths, weaknesses, opportunities, and threats. One of the zoo's main strengths is its partial ecological support, which can further be enhanced. However, a significant weakness is the inefficient use of resources leading to unnecessary waste. Building on insight from our SWOT analysis and sensitivity mapping, we identify key objectives that informed our strategies. Our primary focus areas are climate resilient measures and water quality and management, both crucial for optimizing the zoo's resource efficiency. Under climate resilience measures, we focus on 2 main strategies: microclimate optimization and flood and drought adaptation. For microclimate optimization, strategically planting trees will reduce ambient temperatures, provide shade, and minimize UV exposure, creating safer outdoor spaces. Green corridors can further mitigate the urban heat island effect, improve air quality, and support the biodiversity. These efforts not only improve comfort within the zoo, but also enhance the local ecosystem. For flood and drought adaptation, permeable pavements and bioretention systems will manage rainwater more effectively by allowing it to filter through surfaces, reducing runoff and replenishing groundwater. Underground retention tanks can store excess water for use during dry periods, reducing reliance on external water sources and promoting long-term sustainability. With regards to our water quality and management objective, we identified 2 key strategies: pollution and erosion buffers and stormwater harvesting. For pollution and erosion buffers, bioswales and vegetated buffers will filter harmful pollutants before they reach water systems. Riparian buffers positioned along waterways will slow water runoff, reduce erosion, and enhance water quality by capturing contaminants. For stormwater harvesting, rain gardens will improve soil infiltration and support water-wise planting, reducing surface runoff and aiding groundwater recharge. Urban wetlands will help capture excess stormwater, reduce flooding, and act as a natural filter, improving water quality and providing valuable wildlife habitats. We also identified 2 key objectives for enhancing the user experience: community engagement and design, and wildlife connectivity solutions. These objectives focus on improving how people and animals interact within the zoo. Under community engagement and design, we developed 2 strategies: inclusive green spaces and participatory design. Inclusive green spaces will create public accessible areas that promote social interaction and engagement, fostering community participation. Integrating social infrastructure into functional spaces can transform them into environments that offer both social and health benefits. For participatory design, we plan to introduce public and educational programs to engage visitors, as well as immersive experiences that encourage active involvement and interaction within zoo spaces. Lastly, under wildlife connectivity solutions, we focus on 2 strategies, including designing wildlife corridors and habitat creation. Designing wildlife corridors using green spaces can provide safe pathways for animals, reducing the risks they face in urban areas. Habitat stitching will connect various green spaces, supporting biodiversity and creating diverse habitats for fauna. For habitat creation, preserving existing vegetation and planting new greenery will help protect and enhance habitats. Designing spaces for coexistence between humans and animals will create environments where both can benefit from shared green infrastructure. Here we can see the direct connection between our sensitivity zones to our objectives and strategies. In conclusion, it is clear that the Pretoria Zoo must evolve to solidify its role as a key instrument for biodiversity enrichment, advance conservation efforts, and reconnect urban dwellers with nature. Our assessment has highlighted several key points. The zoo's role has evolved over time, and it is essential to effectively communicate this transformation to the public. Preparing for climate change is vital to ensure the zoo remains resilient and sustainable in the long term. Additionally, the zoo has a unique opportunity to lead the way in urban water conservation practices. Increasing indigenous biodiversity would offer valuable water-wise alternatives to the existing plant palette, enhancing the zoo's ecological value. As urban dwellers' needs continue to shift, there will likely be a growing demand for greater access to nature. Through careful mapping and strategic planning, we have identified crucial areas for improvement and outlined strategies to increase the zoo's impact and to ensure its continued relevance in the future. By addressing these challenges, the Pretoria Zoo can continue to thrive as a valuable resource for both the local community and the natural world.